an example of face recognition, but in any kind of the system that you're going to use, whether it's medical or other kind of classification systems, always you start with something very trivial, right? You start with the image capture, and from the image capture, you will detect the object that is of your interest. For instance, in this case, we are taking the picture of the face, so we are capturing the face detection, or we are detecting the face. And then once the face is detected, you have to align it. I mean, in most of the new networks, they do it automatically, but if you want, you can align it, right? In case of medical images, it's likely that you want to register and align it, and then you do that. And after that comes the extraction feature, the feature extraction. Whatever is relevant for the task at hand, you extract those features, and then you try to compute the comparison between the features. So, and very often in the case of biometric systems, what is there is that it's the database that would have the enrollment samples. For instance, the images that you are captured during your Aadhaar card enrollment, or your the first time you have gone to the doctor, and then you are given your image for the first time, and so on. Okay, and then in the case of face recognition, what it would give is it would give out the subject ID. It would say, okay, this is the person A. Or in the case of the medical images, it probably would say, okay, this image has COVID or not COVID, right? So it's a analogy. So what happens in the most modern systems is that somehow this whole pipeline is in one network. So the feature extraction, the alignment, extraction, and comparison all can be combined, and the database is outside of that, and database is used for the recognition part. Now, if you break it down a bit further, so this is how the whole classical system would look like, right? So you have a face image, and then you extract the region that is very relevant for you. In our case, we don't need the hairstyle, we don't need the color of the shirt, so we can eliminate all those things. And from that particular image, what you do is that you start extracting the features. In this case, I've taken a couple of filters that I'm using. On the top, you see that there are 4 or 5 filters, which is the filters that captures different directional patterns, different edge patterns, and so on. And then you get a final image, which is somehow in the part shown here. And now dealing with the images is quite difficult, right? So it's a huge space. It's 1 megapixel all the time. 1 megapixel, dealing with them is challenging. So what we do is we go for something very small here. Now, if you use a deep network, what happens is that this filters and this one is integrated into that. What you're going to get is you're going to get this embedding space here. So this could be 512, 128, 256, depending on what kind of network you're using. Okay, if this is the given system, let's just recap again what kind of attacks are we talking about. So let's start with this data capture, right? The whole pipeline remains the same. Now, if I start with this one, I already told you that there are at least 3 different attacks that I can think of. I can think of the attack which is overriding the signal processor, and then overriding the comparator, and then the final is the overriding the decision module. Now, more recently, what has been very active area of research is this: how can I modify the reference template so that I can attack the database itself? How can I modify the probe which I have control on, and how can I modify the score? So all of these are different areas of research by themselves, and there are some works which are talking about how to unify all these different attacks. And then in addition to that, I also spoke about this leakage attack, right? So the leakage attack is nothing but if I have something that is coming out of a database, how much can I infer that this is Arun or if this is somebody else, right? So it's all about finding out the information from the database in an indirect way. And then, as I was already mentioning you, there is this new area of research which is called this injection attacks, which I think we have touched upon it partially in morphing attacks, partially in deepfakes. But what we'll focus more is on the physical attacks, which is called as these presentation attacks. And again, there is a number of resources that is freely available that you can make use of, and then you can use it for understanding all the terminologies, and then try to create your own methods for detecting them. Good. So then we just now spoke about morphing attacks. where they come on the top, right? They're dealing with the storage space, whereas the presentation attacks deal with the input space. Okay, so now if you take any kind of impersonation attacks, what do you mean by impersonation attack? Any person trying to say that it is somebody else, right? So I might be going in and I might be telling that I'm Arun, and then try to give the images that are relevant to him. Okay? So a simple example is the fingerprint. I'll tell you why fingerprint. I'll show you an example why we can consider the fingerprint, and I will also use fingerprint as a use case to show presentation attack detection. Now, if I look at this one, so creating such an attack is not very difficult. So whenever you are taking a fingerprint, all we are dealing with is we are dealing with this minutia points, which are computed from fingerprint, right? So the minutia point for to understand that very simply, so a fingerprint looks like this. If you look at it, right? So then I can say that there is a point here, there is a point here, let's say crossing points here, there is another point here. So all of these are nothing but if I just ignore the lines, they're nothing but some points, right? So if these are some points, can I not use these points to recreate some new fingerprint? Something like this. So all I need is I need to have some kind of random points. From random points, I can create the data set. I can create a new image. So that would mean that it's not straightforward as I am saying here, but then you need to do some processing, some mathematical operation, but you can still come from random points back into this kind of image. So which means as soon as I have that, what I can do is that I can reconstruct the fingerprint image. And also applies for the face as well, right? So if I have some features, I can go back from feature space to create the image space. And once I have this, so what I can do is just take a 3D print of that, or just put it on a silicone mask, the jelly that you use for making cake at home. There's baking powder and some combination of some flours and so on, starch, and then you can just press that one on top of that. And as long as I press on that, so I can create a new sample, and this new sample I can present it back into the system, right? So all I did was like to represent myself as Arun, I just went to the database and then I captured every single point that I could possibly, and then create the sample, reconstruct it, create it, and then create the physical sample of it, put it on my finger, put it back, right? So it's that is what we are talking about. When we are talking about this fingerprint attacks. And now, if I'm able to smartly use that one, instead of capturing it, I could also push the sample straight away at this pipeline where I can extract the features, which means it becomes injection attacks. So, try. Are you able to understand the difference here? So, if I'm able to create some physical sample, then it becomes physical the presentation attack. If I'm not doing that, I'm just sending it to the channel in between, then it becomes injection attack. Okay, so now what are we interested in? We are interested in understanding what is this presentation attack. Why should we be worried about that? So in the synthetic content, we saw that there are a number of tools and techniques available to create data, which can be used both for training and also for fooling the system. But in the case of physical attacks, it's slightly different, right? So the difference comes from this angle. So as you can see on the top left corner, you see that a person is holding the image in an iPad, and then you can present the iPad back into the system and say that, okay, I'm the actual person, let me inside. Or you could also do it with something very trivial. You print a picture on the page on a regular A4 paper, and then you try to warp it around your face. Now, because this has 3D, so the system will not be unable to distinguish between whether it's a real sample or it's a fake sample. And now you can tell me that, okay, well, it's quite easy to detect because yesterday we saw a technique which had blinking of the eyes. So if I can look at the blinking of the eyes, I can say that whether if the person is a real one or a fake one. And then there have been some works which talk about this particular aspect where they have taken the face image like this, printed on a paper, cut the eye region, put it on the face, and then blink in front of the system. so you can still get through the system there, right? And of course, when you have some more money, which is what is shown here, right? So you see that it's looking at the area in the eye, and then you have this warped face. You see that there is a difference in responses, which can be used for detecting the attacks. Okay, and then what happens if you have some more, let's say you have some money lying in your account extra? You can do something like this here, right? So you can create a mask of yourself, and this is not very expensive mask, the one that is being held there. So it costs less than $20, so which is approximately 2000 rupees, less than that. Yeah. So that's all you need for creating a mask. So if you want to attack any of your friends' bank account, uh, assuming that the system does not have a attack detection mechanism, so you can do it with 2000 rupees. And then in addition to that, you could also create this kind of 2.5D, 3.5D representations, such as in this bottom image, right? You have partially the face in a particular frame, and then you match your clothes according to the frame, and then it looks like it's a full image. Make sense? And then there is a different area along that where we can talk, depending on how much time we manage, we'll talk about that. This is all the most common attacks that you see in the face recognition. Okay, so is this something new? This has been there for a while, right? You have seen all these movies where they kind of scan and then put the create a new sample. Like here, they're creating a mask, and then the mask is being used for somebody else, right? So this is not something very new. It has been there for a while, and then now the goal becomes how to detect them. Right? For the case of the face, it's slightly relatively, let's say, easier than some other modalities. But then comes also the other aspect, which is about this fingerprint. A lot of us leave our fingerprints everywhere. If you just look at your smartphone right now, I can guarantee you that there are hundreds of fingerprints of your own fingers lying on that smartphone, right? So now once I have that fingerprint, all I need to do is that spend less than, let's say, 100 rupees to create a new fingerprint model, which can be very easily done, as you can see here. So you take the fingerprint from here, put it on a latex sample, and then you lift it back. Then you see that there is a small thin layer of fingerprint that is coming here. So the moment I have that small thin layer of fingerprint, I can use it for attacking. Good. So then in that case, what are we interested in? We are interested in detecting the imposters and the people who are concealing the identity. So I might be doing it for the sake of not disclosing myself, or I might be interested in pretending as to be as somebody else, right? So the presentation attack detection is all about detecting the biometric. It's about the biometric capture subsystem where it can detect if this is an attack or if this is not an attack, such that the other operations are not impacted. Now, why should we be worried about this system? So if I'm having a biometric system, here is an example from a data set which is quite popular in this area of research, where you see that the images that are actually from non-mated samples, which means me compared to Arun, are in that area of that orange region, and me compared to myself is in the region of green region. This is how the system should work, right? So that's what we decided and then discovered yesterday, that the DET curve always represents this matrix. So what happens in the case of the presentation attack is that if you do not have any measures in place, anytime I'm trying to attack the system, it will give me a very good score. Me trying to go as Arun will give me a score which will accept me as Arun, right? So which means the scores that we are getting in that kind of attempts will lie in this area which is in green, right? So the blue one is the mated comparisons, which is actual comparisons, and the green one is the mated comparison. Now, irrespective of where I'm going to put the threshold, so if I'm going to put a threshold on this one, so the ideal threshold is somewhere here, right? Which means all of my presentation attack attempts have gone through. which is a very unfortunate situation, right? We don't want the security to be compromised. Now, what do we do next? So we need to somehow make sure all this distribution that is lying in this green area should be discarded even before they come to this system. So that is the idea of presentation attack detection. Now, if you look at there is this freely available taxonomy slides, which is on this particular link. You can download it when you get the slides. And in this case, what it defines is that a presentation attack instrument is it's a biometric characteristic or an object used in presentation attack. Now, why do we say it as presentation attack instrument? The instrument can be different kind of instruments, right? It can be paper, it can be iPad, it can be something else, and so on. And then within that, you have this lot of species which they define here. And then there is a discussion about this presentation attack part, right? Where we are talking about, is this artificial, is this human, or is it any other natural devices that are being used? So in the case of artificial, what they say is that, is it completely artificial or is it partially artificial? Let's say tomorrow you create a robot which has your skin texture. So are we talking about that one, or are we talking about only part of the face which is artificial, right? And then we have the human part where we talk about lifelessness. Specifically, there were some instances where the money was transferred from one person to another person right after the death before it was declared, right? So now we are talking about a person who has passed away some time ago, let's say a couple of hours, and then everything is still operational because the biometric characteristics are intact, the fingerprint is intact, the face is intact, and I could still use it to authenticate and transfer the money, right? So that is what we are talking about, the lifeless, whether it's lifeless or it is lively. And then how much of that is altered? Is it partially altered? For instance, there was a case when one of the sisters were planning to go, I think this happened in Vietnam, so we're planning to move to US, and one of the sisters had not been in US at all, and she was planning to go there, and she was stopped in the border, telling that she was already inside US, and I think that at least the story goes that way. And it was discovered later on that the other sister who was in US, she had used the identity of this person by cutting and pasting the fingerprints here, right? So these kind of things can easily happen, right? So that is what we are talking about, altered fingerprints. And then there is this also this non-conformant category, and then coerced category, which means that I'm putting a gun to the head of somebody and then I'm making them to present on themselves. That is another category of attacks. And then comes the conformant attacks, where I'm willingly trying to attack the system with another person, right? For instance, if I want to access the supercomputing lab in MNIT and I don't have access, maybe I will ask my pal, and he will also let me in as me as himself, right? So using his ID card, and he will let me in. Okay, so these are some of the kind of the attacks that we are talking about, and then I'll first give you a motivation about what can we do to detect these attacks without even using deep learning. So this is based on sensors. So here, if uh, you see that in any kind of cameras, you have a couple of optic sensors, right? So there is a camera which has number of lenses, number of imaging optics, and then the image is formed on this sensor, right? So irrespective of what kind of capturing system that you're using, roughly the architecture remains like this. And for those of you who understand a bit of optics, you see that each of these component has its own role. For instance, one is used to capture the ambient light, or it focuses the scene, and the other part is somehow uh, making some area in focus by putting different lenses. And all of that information is collected onto this sensor, which is on your camera. Right? It's in your smartphone. Now, if you take a very close look at that one, you see that the colors are alternating, right? So you see that there is R, G, G, and B. Let me just zoom it again. You see the pattern here? It's repeating pattern, right? So if you look at this one, it's the combination of R, G, G and B, which means that your one pixel is made from four of those units. So all those four RGB will give you three values, which is RGB values. So that is what represents how white a particular pixel looks in your photo or how dark it looks in your photo, right? And this construction is very universal. So the combination might change in some sensors. For instance, it might be RBBG, but usually it's RGB. So you're having four units for capturing one pixel. Now, what does that do? So if it's able to capture such patterns, now in each of these individual image, if you just decompose it into R and G and B, you can see that the information that is in these two images are slightly different. It's an idea, right? So you agree with me that it's that one is a bit lighter than this one, but it looks very blurred, and this one also looks very blurred, right? So when I combine all of these three things together, that's when I get this image, which is like this, right? So what am I going to do now? So now if I know that there is a certain pipeline that is happening in this one, and I know that each channel gives me some complementary information, what I can do, I can create a method which does not need any kind of deep learning. Of course, you can plug in deep learning here, but the idea is what I'm trying to explain. So what I do is like I take this input image and I simply blur the image. And once I blur the image, I try to take a difference between those two. Now again, the ideas of reconstruction that we are talking in the morning, the ideas of residual in the morning, it is exactly the same, right? I'm trying to introduce some Gaussian noise. I'm trying to make it blurred. And once I blur it, I get an image which is residual here. So if you look very closely, the information that is not available to the naked eye, you can see it here, right? So now I can get such information for each channel, R, G and B channel. So and then once I get that, what I can do is that I can chunk the whole image into a number of different blocks. And these blocks are again, you can configure by yourself depending on the application. But in this case, we did 4x4 blocks. And for each of these 4x4 blocks, what are we doing? We are computing the amount of pixel that varies across the block. Nothing fancy here. Everything is basic signal processing. And once I do this, I can sum up the whole energy distribution. And once I do that, I can have a classifier here which says whether it's a bona fide image or it's an attack image. And this family of approaches can work only when you have the sensors at hand. If you do not know your sensors, then probably they will fail. Good. So just to motivate you for not only looking at the deep learning, but also to understand the signals from physical perspective, from the signal processing perspective. Here I show some images where if the raw image is taken and then the median filtered image is taken and the residual is formed between them, if it is actually a live image, the residual is almost zero. You see that it's a completely black picture, right? If it is not a picture which is coming from a live person, let's say if it's an image that is coming from a screen, and the screen will emit you some differences. You see this patterns here. There is this, I don't know if you're able to see it from there. It's like this moid pattern, yeah. And then if I take a difference between the image and the median filter version of that, you can start capturing these patterns here, right? Maybe it's a bit dark there, but you can look at the slides when I share them with you. Okay, and then what happens to the other kind of sensors? Maybe you say that, okay, Dell was very easy. What happens to the Samsung? Again, you are able to capture them. And then what happens to the paper? Even in the case of paper, you can capture the patterns. So once you do this, if you are able to see at this graph, now you can see that all the correct images, the bona fide images, which are real images, so they are classified properly. and then everything that is attacked, they're also classified properly here. So this gives me a decision boundary between so many values. I can now set if the energy is at 2, if I set the threshold at 2, then I can see that the error rate is around 5%. Right? So now I can say, okay, maybe I don't like 2, I'll set it as 2.5. So if I set the value at 2.5, the error rate is less than 5. So which means by doing simple signal processing schemes, I can get a wide variety of decision boundaries here, which can of course be used for fusing. So I can also combine multiple decision thresholds, right? And again, you can see that at this particular point of time, I get the lowest error for all combinations. So this is able to detect both the paper, the screen, and the screen. So two different kind of screen, one different kind of paper attacks. Okay, so that is something that is part one, and then I'll motivate you for going towards. Again, this at this point of time, this work was done in 2016. So at that time, we were looking at the hardware level security. And now we can go to the next part, which is on the ID cards, and then I come back to the fingerprints later on. But in the case of in India's case, it's Aadhaar card that is quite popular, right? For every single thing that we are accessing, let's say to book a hotel, to avail a government service, and so on, we always use the ID card. So, what can happen on the ID cards? Now that we have seen a lot of generative content from yesterday, so if I collect hundreds of your Aadhaar cards, I can create a synthetic ID card, right? Synthetic Aadhaar card. And once I do that, what I could do is that I could simply print it on a very nice paper, very similar to what the government is providing, and then I can take it with me to show that okay, I have a valid ID card, valid Aadhaar card. And very often in many of the services that we are going, they're not verifying if it's an authentic ID card. Or you could always tell that okay, I left my ID card at home, so I have my printed ID card here, right? Or a photocopy of that one. So in some cases it's okay. Let's say if you're going to a restaurant, it's okay. But if you're going to access the bank system, then they need to verify it, right? And then how can they verify it? First, they have to determine all the security features. And now your generative model is so much capable of integrating them into the card, then it will be a problem, right? So what do we need to do? So then we will need to detect them. And then here I give a motivation for using the system, which is based on the simple pixel-wise network. Okay, maybe this. Okay, let me just do this. Okay, in this case, now again, very simple idea. So we have the ID card, and then every time I'm presenting the ID card to the system, what first thing I need to do is that it's not in the normal shape. It can be tilted, it can be rotated, and so on. I need to align it. I do a simple alignment and make it straight. And after that, in this work, what we did was we simply took the convolution layers. We added a couple of layers. Okay. So we added a couple of layers, and these layers now by now you are all recognizing them, right? It's a convolution 2D layer, and then it's a batch norm, and then there is a ReLU, and there is a max pool. So nothing complicated than this. And then we introduce something called as the transition layer, where we introduce the pixel-wise supervision, which means at this point of time, I can say every single card which is valid, authentic, versus the every single card which is not authentic, I can label it. And this labeling is not done manually, it's done automatically because I'm looking at every single pixel, right? I say that, okay, these pixels are real, these pixels are fake. Once I do this, I can simply learn that two transition layers, and then I can make a decision saying that whether it's bona fide, it's unmodified ID card, or it's a modified ID card. Okay, so the modified ID card would mean that it could be partially modified or it could be fully modified. So what is partially modified? For instance, if I have a Pranav's ID card and then I want to use his details to open a bank account for laundering the money, all I need to do is I need to replace my face photo on his ID card. So this is what we are talking about, partial modification. And then some other time maybe there is a hotel in the city which will not allow people less than 25. So all I need to do is that I need to modify my date of birth, right? So this kind of subtle modifications need to be also identified. And in this case, this network was able to do that. I did not add another work which was done after this. There, what we did was we took the features from this point. At this point, we cut off everything beyond this, and then we added a transformer on top of that. So that means that all the features that we were getting from beforehand, probably I can show a picture in the end, and then you can refine it in the second level. So the idea is again, the idea was quite simple. So whenever we are looking at the manifold space, we saw that the real was like this, and the attack sample were like this. So which is overlapping, right? So if I add one more network on top of this by cutting off this one off, so I can say that from this one and try to separate them. Now when I do that, so I got a better boundary like this. That means I can now say that okay, everything that is lying here is bona fide, everything that is lying here is attack. So this is not the main point. The main point is that look at your features as display, try to analyze the features in the embedding space, and then looking at those features, you can come up with a technique to address those problems. Okay. Again, going back to the latent vector. Okay, how much time do I have? Another 30 minutes? Yeah? Okay. Good. Okay, so now let's take a simple case of fingerprint presentation attack detection, right? I showed a couple of images yesterday, but I'll give you a motivation about how we can detect it using the VIT transformers. Before I proceed, any questions so far? Anything that you are wondering? Motivation, approaches? So I'm trying to give example of classical approach and also the deep learning approach, right? So you get an idea of both cases.
I have only one query. That particular project was done, right, on ID card.
Yeah, yeah.
So how could you get? Either you have to manipulate and create the ID cards. Yeah.
That's a very interesting question. So the question is about how did we get access to the ID cards? For the real ID cards, we asked a couple of people to give their ID cards. We captured their picture. For the attack data, we had to capture them independently. So the student was sitting and presenting it on the computer screen and then capturing every single thing. So that is one. And there are two other data sets which are publicly available, which are again from one from Chile and one from another Asian country. So there are only three data sets that are publicly available, which is very.
Those are different. If they are from different countries,
Yes.
then their restriction is
Very, very interesting point. So for those of you who are looking for a new problem to solve, this is unsolved problem. So right now, all the European Union has some kind of similarity in the ID cards, but the ID cards from Aadhaar and the ID cards from European Union are very different. Right? So that's what we are talking about, the generalization problem. So there are some problems that are solved, which is not tested on all different kind of ID cards. And also the second thing is how can we unify, how can we make it independent of ID cards? So that is very open problem. So if you are running out of ideas, so you can take this up and then try to investigate this.
Even the placement of the variable can also be different.
Yes, that is also very, very different. So the ICAO compliance documents define it in a certain way, such as passport. They are always standard, right? Irrespective of what country you go, the name is placed in a certain order, the face image is of certain size, and so on. But when it comes to let's say even take the India, the driving license that we are getting. My driving license has a picture which is 25 years old, right? So and they are not updated in the picture, and this is a common problem,
Saudi Arabia, they are writing from right to left.
Yes, that is another problem, right? So there comes the text. Okay, that is also very interesting point. Yesterday we did not discuss about that. So in the example that I gave about transformer, I told attention is always from left to right. And I was expecting somebody would comment on this one. Nobody commented now. So in the case of the Arabic languages, right, the attention is from right to left. It's not left to right. And that's the same thing in ID card as well. How the placement, the fonts, and the language. Language aspect is also another important point, right? So we not only look at the image characteristics, but we also look at the demographic data on the ID card. To say that if you are saying that, if I'm saying that, say, I'm a 10-year-old boy on my ID card, it does not really correlate, right? So you should also look at the date of birth with the face image. So we are extending that work in those directions, but there is a lot of scope in that area if you are interested in. There are in fact two competitions being organized, one in ICCB and there was one in IJCB this year that's already done. So this is dedicated to detecting the synthetic ID cards. So if there are some smart students that want to work on this one, that might be very interesting challenge to participate. Okay, now let's take the case of the fingerprint, right? So I'll come back to the motivation here in a bit. So you all remember that how easy it was to collect this fingerprint or lift the fingerprint. So I can create it from this random points, or I could go simply take one of your phone and then lift the fingerprint from that. And lifting fingerprint is also not complicated process. All you need is like you need some kind of powder. People working in the forensic domain, you know that it's very easily available. Even if you don't have, you can take the charcoal coffee powder, grain it very fine, and then dump it on the smartphone. Just brush it, lift it.
Just use a talcum powder.
Just use a talcum powder. Talcum powder is also quite effective, and then you can lift the fingerprint, right? So this has been a very active area of research for a lot of years. Now what we want to do is we want to detect those images. Is it really coming from the person, or if somebody has lifted it and then created a new fingerprint? So in that case, what we wanted to look at is I'm going to give you a motivation about using CNNs and using DIT. Each of them have their own advantages and disadvantages. In the case of CNN, they are very efficient in extracting the local features because they work on local receptive fields. And then in the case of, and then they are also very capable of capturing the spatial hierarchies. They are computationally efficient. They are also very good for small data sets, right? So we have this motivation why they can be used. And then in the same time, we have this data efficient image transformers. And these are based on the architecture of transformers, which is again based on attention mechanism, and then they capture global relationship. And both of them have their own unique roles, right? And then is the idea of this architecture itself. So yesterday we spoke, or we briefly discussed about how the tokens are processed in vision transformers. Oh, sorry, in the transformers. Now, then I told you that in the case of the image, it's exactly the same idea, except that we are chunking the whole image into small parts, like here. And then I treat every single part of that image as a word. So the whole image is my sentence, and then every single part is a part of the word. And using that, I could simply put into the transformer model and then get the embeddings out of that. And then to maintain the contextual relationship, we also spoke about this positional encoding, right? So I know that this area should remain here. It cannot be here because it does not respect the semantic meaning. It does not respect the context. So I'm going to enforce such thing using this patch embedding and the position encoding, and then it's the regular story. So we have a transformer encoder, we get the MLP, and then we can identify which class it is. Good. So now if I start with that, what is the architectural change in case of the DEIT? So it's following the VIT architecture. And yesterday when we were talking about this multi-ed attention, right? You remember we said that we have single ed attention, and then I have multi-ed attention for maybe specific to language, maybe specific to semantics, and so on. So it's the same idea here. So now what I'm going to do is that I'm going to learn a network, and then this network will be transmitted to a smaller network, which is a distal network, which is the teacher student association, right? So the teacher will train the student, will the student will get all the necessary important knowledge, and the important knowledge is used to classify the two images. Um, for those of you who are more interested in this area, is also to look for not interested in this area, but those who want to explore it a bit further, so you can try to understand this CE laws and the teacher laws. So they are again determined for learning the training the teacher and training the students. Okay, so then if we take this base architecture into picture, so what we are looking at is we are looking at a number of different configurations, and these all configurations are called as base configurations, and then everything is with the distal configuration, right? So you have the teacher that is trained, and then we discard the teacher. We only take the student, and the student has these kind of parameters. You can see that the hidden activation is JLU, which is another variant of activation layer, and then you have the size which is for 224, 224, and 384, which means your image can be up to 384 pixels. And rest of the parameters are very similar, right? So the number of attention heads are 6, 6, and 12, and in this case 12, 12, and 12, and the patch size is 16, 16, and 16. So why is that very often we take this patch size as 16? Because there was a paper which was written as I don't recall the title of the paper. It was a very nice title. A picture is worth 16 cross 16 patch or so. One of these paper. In that paper, they have described all the configurations, and they show different results where you see that the patch with 16 cross 16 is performing very good. Okay, and that's what is used in this architecture as well. Okay, so what was our goal of this work when we did this was to look at how good are these CNNs in generalizability as compared to the vision transformers, and specifically for the reason that we have this known attacks where I know how the fingerprint was produced, the fake fingerprint. In cases where I don't know how it was produced, how well does this approach work? Okay. Um, and for this case, again, there is this very nice data set that is released for public research. So if you are interested in getting this, you can write a mail to them and they will give you this data set. This data set is also part of the competition which they run every year or every second year, and you can submit your algorithms and they evaluate and then write a paper about that. So Live Day 2015 is quite of kind of old data set, but it's still very useful, very valuable. And then 2019 is another data set, and there is a new version of that which is 2021. So every time they run the challenge, they add some new challenges into that. And in our case, what we wanted to do was we said, okay, let's show the systems some data, which is partial open data set. And in the other one is true open set, which is I will not show you any data in the training. I'll use them just in the testing set, right? Okay, so in this case, if you look at the images, some of the images are quite obvious for us. If I show you the images in the bottom row, you will always tell me that, okay, most of them are synthetic images. They are recreated, right? But the machine still struggle to identify those ones. And very often when I'm crossing the border, when I come to the immigration system in India, the first thing I do is I give my fingerprints to the officer, right? And there, if the machine, it's actually the machine that's making the decision. So, and if the machine can be presented with such a sample, then we are in trouble. Okay, that's the motivation. But here, if you look, there are a number of different kind of systems that are used to create these artifacts, right? So, for instance, here, so you have all these normal images on the top layer here, And then you have the attacks, which are created using LaTeX, EcoFlex, mixing the two different sessions, and a combination of multiple these things, right? And again, there is this third variability, which is what device are we using to capture this here. So, and again, these devices are very easily available on Amazon and so on. So you can buy one of those if you want to create your own data set for your research. Also less than 2,000 rupees or so, very less cost. And all the materials that you need to create those samples are also very easily available. Okay, and then here you see that there are three different sensors that are being used. One is called Greenbit, Orcanthus, and then Digital Persona, and each of them capture the images of different quality, different resolution, and so on. Now, within the capturing pipeline here, you see there are three different types of capture, at least two different here. So one is optical capturing, which is nothing but it flashes a light and then it captures the reflections, right? And the second one is the thermal swipe, which means that there is a sweep of fingerprints and then it constructs the fingerprint in the end. So the idea is that the data set represents quite unique challenges in terms of diversity of capture sensors, diversity of samples, diversity of materials used, and so on. All right. So what happens in the live at 2015? Should we just ignore everything that has been done in the CNN network and then just move to transformers? Instead of that, let's try to take a look at what is happening in all the different networks. So here, I think 21 different networks were evaluated, and if you look at the system here, we took the network as it is, trained for some other purpose, and then use it for our purpose, which is called transfer learning, right? And then just by replacing the final two layers, and then we retrain the whole network by discarding all the weights and then defining the weights for those particular tasks using the softmax layer, and then we see that the error rates start dropping down. The overall trend, whatever was in green, is now becoming lesser, right, in the case of orange. So which indicates that if you are able to train your own network with the data from scratch on, it will be able to give you better results. And then we also wanted to try out with different kind of activation functions, softmax versus sigmoid. So what happens with the softmax versus sigmoid is that the results drop even further. In many cases, across different architectures, it's still very consistent, right? It's not increasing in except one or two cases, which tells that CNNs are still capable of doing such kind of jobs, right? So it's still a popular model. Uh, and the other thing that is quite interesting here to note is that you have wide variety of networks starting all the way from VGG networks here to something that is more recent, which is efficient net, which are very compact, including the mobile net somewhere. It should be here, the mobile net, right? So the task can be solved with very big networks to very small networks. Good. And then what happens if we take all the same CNNs which are trained on the previous case and then tested on new dataset which is unseen from beforehand? And in this case, we see the same performance trend. Two of them spike very highly, and then most of the other networks are still okay. They are giving you around 30%, less than 30% error rates. And then if you do the retraining using softmax, that reduces the error significantly, and the biggest gain can be seen here, right? The two of the bar charts here have dropped very significantly to close to 10. And then if you do it with another activation function, you can again see that the error rates come down quite significantly, right? So the idea here is that one, the networks are completely not useless. Now, as soon as the transformers come, you don't have to jump into transformers. The old networks are still very useful. And the second thing is that if you look carefully at your data, you can choose the network that is more relevant for this. Okay, I'll not give you the numbers here, but then I just wanted to show you the complementarity of the networks. So what happens in the case of multiple networks? Maybe one network is very strong in detecting attacks based on EcoFlex, one kind of generation, right? the other network might be very strong in detecting the images that are printed. So if I have such kind of complementarity of networks, if each of them are able to capture subtle information significant for one task, I can combine all of them now. Simply by combining all those top 5 performing networks, I see that the performance goes to 6.20. And by combining top 10 performing networks, I get an error rate of 6.18, which is 10, almost like tenfold improvement here, right? So it's 15% here, you go down to 6% here. And if you don't want to do all those determining which network is better, which network is not good, you simply dump all the networks together, then you get an error rate of 6.34. But this is a bit overkill, right? So you don't want to put 21 networks to solve one simple problem, because then you are increasing the computation power. Okay, so the idea here is to just tell you that by doing some simple combination of networks, we are trying to impose what is called as the information theory concept, which looks for complementary information, and you can fuse the information together. And what happens with the case of here we looked at 21 different networks, right? And in the second case, I'm simply using a VIT transformer. When I'm using the VIT transformer, the error rate is around 4.8%, 4.79%. The lowest error is in this case. Good. So let's try to take a look at this one. So again, remember that because we can't optimize both FAR and FRR or BPCR and APCR, I try to fix one of the error metric here, like 5% and 10%, and then I measure how the performance is. And if you look at this one, 2015, the data set from 2015 was so much high, and 2019 it dropped down to here, and then in the case of DEIT, the error rate were pushed quite significantly. Okay, now there is no reason for you not to combine the transformers and the CNNs, right? You can combine because one captures the global information, the other captures the local information. So I can combine both of them. Good, and then we have this the idea of explainability, which we will talk about tomorrow. But just for the sake of curiosity, here you can see that if you are using any random network, the attention is spread everywhere. But if you are using retrain network here by relearning, then you see that the error rates lie around. Sorry, not the error rates. The attention lies in the key areas of the image. So which is what is shown here, right? By simply relearning, you are able to focus on task-specific activities. Okay, and then let's take a look at the DEITs. If I take the vision transformers, I see that the attention is much better. Now I'm having the information which is pointing to the areas within the fingerprint rather than the areas outside the fingerprint. Okay, so what happened between the seen materials and unseen materials? So in this case, I'm using the training set which is digital persona, but the materials are different. The capture sensor is the same, the materials are different. So in that case, you see that the error rates kind of vary drastically. So whatever was on the top area has now increased, the areas have shifted up. And the same thing when I do it on the next part, right? In the case of DEIT, it is whatever the error rate was around 4%, it's now gone up to 11%. What does this indicate? I told you that VITs were very good. They gave me the error rate of 4%. Now I'm telling you that the error rates are gone to 15%. Does it tell you anything about the aspects that we are talking about? Overfitting, generalization error, right? So it saw the data and it could fit it to that data. Now suddenly I'm introducing a new data which it has not seen before, and as a result of overfitting, it's failing here. So the generalization problem is still an open problem. Good, and then there is a number of different aspects that we discuss in that book chapter, which is on Handbook of Anti-Spoofing. There you can see that the error rates are still quite high. So if you look at this table, right, So you see that we are talking about this 46% error rates coming down to 26% error rate, but still there is a scope to improve from 26% to 0%, right? So for those of you who are interested, maybe this is a topic that you can think of. Okay, I think I'm running out of time now, but I'll just want to also show you one other thing um, where we can combine the ideas of deep learning and the classical learning. And in this case, what we are trying to do is that we are trying to use by work by one of our colleagues is to use what is called as leave one out protocol. So if I have 5 different kind of attacks, what I do is I use 4 attacks and then I leave one fifth attack aside and then try to train a model on 4 attacks and then test on fifth attack, right? And by doing that, I can understand the generalization, understand the aspects of this overfitting that we spoke about. Okay, so what is the idea here? Again, the idea is going back to distribution properties. So if I know that all of this normal data is lying in a certain cluster, something that is beyond that cluster is an anomaly for me. The anomaly means that it's an attack. It's not behaving as a normal data, right? So what can I do? So I need to add this generalization capabilities to existing approaches. So one, I retrain the whole system every single time I get new samples, which is very tiring, very time consuming and computation heavy. And then what I can do is like I can take these features and then put it into a new domain and then try to learn something out of that one, right? In that way, I don't have to relearn the whole system. So there were some very good results that were published in the work that was done for face, fingerprint, and speech, and then it also kind of indicated that deep learning is not the only way to achieve good results. So you can still go to the classical learning idea, apply the idea of this Fisher vectors, and then you can still get a good system. So to give you a rough idea, right, I'll tell you how the whole architecture was given in their work. So one is that you have all these feature vectors. Whatever is your favorite feature vector, you can take them here. So in that case, they used 5 different feature vectors, and they concatenate all of them into one single vector. And once you have put all of them into one single vector, you can do distribution learning here, right? So if I put all of the features into certain areas, then I see that they get kind of clustered into one areas. So if they are not clustered into that one area, then I can learn what is differing from that one. And if there is anybody that is aware of, no, oh, okay, you don't have to be aware of this one, but you remember we spoke about this, the distributions. So if I have 5 different distributions, so let's say 1, 2, 3, 4, 5. Now I can approximate an overall Gaussian out of this, right? So I can say that with all this distribution, there is a common distribution that covers like this. Nothing fancy here. All I'm doing is like I'm putting everything as one distribution and learning that. So now you can try to use what is called as Gaussian mixture modeling. As soon as I have this one, so I can start separating it out, right? So if this is a Gaussian mixture, how much is this different from this whole distribution? So if there is anything new coming here, so I can always say that how much different is it from this distribution. So by simply using such old school techniques, they were able to achieve good result. And then once they have that distribution space separated, all you need to do is to plug in your favorite classifier, SVM, KDA, LDA, whatever you want to. And in their cases, they did true unknown attacks where they did not show the images from beforehand. So they just simply put all the images which are unknown to the testing system. And there you see when it is trained on the known attacks, the error rates are quite low, surprisingly as low as 0%. Right? You see this area, the error rate is almost 0, but the moment you put it in the context of unknown attacks, the error rates kind of increase here, right? But still a lot less compared to the errors that they had before. And then if you do the Fisher vector representation again and then try to look at how the features are changing, you see that the error rates are still significantly consistent. They're not going from here to here, right? That would have been a disaster. So now this kind of tells that with simple processing of the data, with simple processing of the attack samples, I can still and classical machine learning, I can still achieve some generalizable results without overfitting. Okay, so I think I'll stop at this point, but before I stop, I just want to give you a very brief overview of one other thing, something that might be of interest to many of you. Uh, I think most of the, at least women here, would have undergone this optical tomography. No, when you go for your tests for medical tests, you're especially when you're carrying, there is a certain technique that is used to image the baby, right? So which means that it's going under the skin layer to identify the um, identifying the baby. So which is a very similar concept, which is called as optical coherence tomography. And in the previous case, I told you that it's very easy for me to lift a fingerprint and then create a fake sample and put it on my finger. Now, if you take the same idea of this optical coherence tomography and you put it onto a fingerprint sensor, now what you're capturing is you're not just capturing the top layer, but you're also capturing the layers inside the fingerprint. For instance, here, uh, if you look at this one, it is exactly the fingerprint, and you see the layers below that. So the first layer is here, the second layer is here, the third layer is here, and all the layers are very similar to each other. Not very similar, they're identical, exactly the same, right? So with this technique, with this approach, what you can also look at, okay, now something happened. Okay, with this approach, what you can also see is that many of us have these cuts, especially when we are cooking. We are cutting our skins. If you are working in the farms, we are uh, maybe having a small cut because of a plant. Or sometimes it might also be that we have some, let's say, warts, like pimple-like structures, and that would always allow us not to identify ourselves very well. But by using this optical coherence tomography, you can still get the images that are below your superficial surface, which gives me two advantages. One, when I have cuts and marks, I can still use it. And the second thing is that if I'm trying to put the fingerprint of Harun on my own fingerprint, then the system can easily detect that the fingerprints, the outer fingerprint and the inner fingerprints are not the same, right? Which gives me the inherent capability of detecting the attacks. And this is also a field that kind of, we worked on it in 2016, 2017, and now we are not actively working on it. But this is how the fingerprints would look like in different layers. Layer 1 to layer 6, you see in some layers the information is very rich. In some layers, some parts of the information is missing, but it appears in the other layer. So you can get this complementary information across all different layers. So the reason I'm just putting it here is that some of you might be working with other departments who work on optics and engineering, or let's say electrical engineering, and then there is this nice avenue of creating new sensors for such applications, right, by combining the.
You are showing is different from the CT scan that we are doing.
This is exactly the CT scan correct?
The layout is
This, yes, this is because the optics is organized slightly differently. So this is not exactly CT scan. In the CT scan, we rotate the thumb, right? In this case, we don't have to rotate the thumb, it's fixed. And it's exactly coherence tomography, but it's just optical part. Sorry, I told you this. It was for scanning the babies. It's actually the coherence tomography. It's the CTMR, CT scan technique. Okay, so there is, I think we can talk. Okay, so now the goal was to introduce you to all different kind of physical attacks that are still possible. So today you saw digital attacks. You also saw the physical attacks.